concepts of heat, work and temperature. So we've all heard of these words, and we've all got our own ideas of what they mean. So let's have a look at them scientifically. What actually does heat mean? What work means? What is temperature? Okay, so heat is basically the transfer of energy from one system to another. So if we've got, this is our system, whatever it is, it's a reaction flask if it's chemistry, or it's a spring if it's physics or something like that. So we've got our surroundings, and our surroundings, well, let's say that's the other system. Or we could have, make it a bit easier, a cup of tea. We've got a cup of tea there, and we've got a hand around it. It's the hand. Okay, you have to forgive me for the hand. That's the hand around a cup of tea. Now the cup of tea is hot. We've all experienced this. Heat will transfer from the hot cup of tea to our cold hand. So if we look at this as a system, this is the hot cup. This is our hand. This is a system we're interested in, the hand, and the hot cup of tea is the surroundings, say, and heat is transferred into the system. Now that will raise the energy of this system, our hand. Now you have to forgive me if this is a bit confusing, but the idea is that heat is the transfer of energy, but it's slightly different to work. Now work is also the transfer of energy, and the difference between the two is that heat transfers energy in a chaotic manner. So imagine all the molecules in my hand. The energy that's transferred from the hot cup of tea will go into the molecules in my hand. They'll get more energy. And rather than my hand just moving away in a certain direction, it'll stay still, but my hand will get warmer. And the reason it gets warmer is because all the molecules have more thermal motion. They will move more, they will vibrate more, and that generates its own heat, if you will. So heat is the transfer of energy from one system to another in a chaotic manner. Chaos is the key to that one. Chaotic. Okay, so just circle that. And that's heat. Can't be used really. All it does is increase the energy of whatever system you're interested in. Now work, on the other hand, is slightly different, because work is it's a transfer of energy from the uniform motion of atoms. And what I mean by that is, imagine you've got a piston. Let's move these down a little bit so we can just explain this a bit better. So move that down there. So if you've got a piston in your system, there we are. Now work is the transfer of energy as well. Okay, so that might be new to some people, probably not, but work is the transfer of energy as well. Okay, but work is the transfer of uniform motion of molecules, if you will. So rather than giving our system here chaotic random motion that we can't really do anything with, but just increases the internal energy, work can be used. Now this is why thermodynamics is really important, because work can be used. So if we increase okay, let's say this is a fuel in here, it's got petrol in there, or gasoline if you're in the US, and we increase the energy there with heat, random motion, okay, random thermal energy, all the molecules move faster, and by increasing the heat of the system we can provide work on the surroundings of a uniform motion. So increasing the energy in this system will cause the piston to move up, so it goes in that direction, and that's a uniform motion of molecules. All this piston is made out of molecules, or atoms of metal, and it moves in the same direction. So that is work. Work is the transfer of energy that changes the motion of atoms in the surroundings in a uniform manner, and that's the standard definition of that. Temperature, on the other hand, is more to do with entropy. Now we'll cover entropy later on, and really temperature is like the random energy that molecules and atoms contain, and you can't really do anything with. Okay, so you can't use it as work. So if you've got one system here, let's get this back up, and all these definitions I'll put up at the side. Let's just move this back up. Well, look at these two systems here. We have got, so this is cold and blue, and this is hot. Okay, these are terms that are used for temperature. Now temperature is not heat. So that's the first thing you need to know. Temperature is not heat. Heat is a transfer of energy. Now heat occurs during temperature is very important for the transfer of energy. So what happens is this here, the hot system, means that the atoms and molecules in this system here have got more thermal motion, more random chaotic motion than the ones in here. So T2, say, and that's T1. And what we're saying is T2, the energy of it, is greater than T1. And what happens there is T2 can transfer some of its energy. So this is T2 here, this one. T2 can transfer some of its energy over to T1. Now T1 doesn't transfer energy over to T2. That can be done, but you need what's called like a heat pump or something like that. We won't go into that, that's a bit too confusing. But the transfer of energy from T2 to T1 is a spontaneous thing, really, because it's got more energy. So imagine energy is flying backwards and forwards between these two, and these are a good way of imagining it is like dodgeball or something like that. So these are transferring energy, and these have got more balls, that's the energy, and they can transfer more over to T1 than T2. And what happens is, over time, okay, so let's go with the dodgeball analogy here, the balls are transferring backwards and forwards until eventually there's the same amount of energy on this side as there is on this side. And when that happens, we have a thermal equilibrium between the two systems. And that is exactly why like things cool down to the same temperature. Or, you know, if you've got a hot cup of tea, for example, you leave it on the side, it will cool down to ambient temperature because the energy will be transferred backwards, because there's a lot more energy in the cup of tea than there is in the surroundings, in the atmosphere. So the energy is exchanged very quickly, and over time that disappears and equilibrates to the same temperature. And it's only because they're sharing the same things, and eventually they share identical amounts of energy with each other, and that's all equilibration is, really. So a bit of a long-winded explanation of temperature, but I hope I've explained the different concepts. That heat is the chaotic motion, thermal motion of atoms and molecules and things like that. Work is the uniform motion of atoms and molecules, and we can really use that. And that's, like I said, this is where thermodynamics is really powerful, because we can transfer heat into work and things like that, and that's really useful. Temperature is more the intrinsic chaotic motion of molecules and atoms that can't really be harnessed, and that's more to do with entropy, and we'll talk about that later. So that's it for now. Bye bye.
That is regarding heat, work and entropy, their interaction and their importance in engineering field. Now next is another example. The data is given like this. Consider a monotonic ideal gas which expands according to the PV diagram, and the PV diagram is given like this: pressure versus volume, pressure in terms of kilopascal. The process is A, B, C and back to A, and volume is on x-axis represented by V into meter cube. The questions: first question, what work was done by the gas from process A to B? From here A to B, what would be the work done? Question number B, what heat was added to the gas between A and B. So from A and B, what is the work and what is heat added to A and B? C. What work was done by the gas from B to C? First A to B, then B to C, what is the work done? Then fourth question, what heat was added to the gas between B and C? Then what work was done by the gas from C to A, and what heat was added to the gas from C to A? So for this A, B, C and A process, we have to find out for each processes work done and heat addition for AB, BC and CA. So first question, what is the work done by the gas from A to B? So of course that is the area covered between the process A to B. This is the area covered between A to B. First is this right angle triangle and then this rectangle. So for that, work done is equal to WAB and that is equal to area covered. So we have to find out the area covered by this AB, this area. So for to compute this area, the difference is 0.6 into 0.2, that is 0.4. That is the width of this area, and height would be the mean height, right? This effective height would be half of this, say 25 plus this 25. So that is 50 unit or 50 kilopascal, that is 50 into 10 raised to 3 Pascal, and multiplication gives us the answer is 20,000 joule. 0.4 into 50 into 10 raised to 3, that is 20,000 joule is the work done by the gas from A to B. Now second, what heat was added to the gas between A and B? So first find out internal energy at A, internal energy at B, that is U at both the ends, W is known to us, and these are the equations for monotonic gas. U is equal to 3 by 2 nRT, PV is equal to nRT, and U is equal to 3 by 2 into pressure into volume. So UA, that is initial internal energy, that is 22.5 kilojoule or 22,500 joule. Internal energy at point B is 22,500 joule. So change in internal energy delta U is equal to 0, and hence finally solve for Q from the first law of thermodynamics. Delta U is equal to Q minus W. W is known to us, delta U is known to us, hence Q is equal to 20,000 joule. So that is the answer of second question B. Now third question, what work was done by the gas from B to C? Whenever the process transfer comes from B to C, what is the amount of work? That is of course the area covered by B to C, this area, that is equal to width into height. Work done by gas from WBC is equal to area. Width is known to us, that is 0.6 into minus 0.2, that is 0.4 meter cube, multiplied by this height. Height is 25 kilopascal or 25 into 10 raised to 3 Pascal. The answer is minus 10,000 joule. Why it is minus? Because here process is from B to C, from right to left, hence work done is negative, or work is consumed for this process. Work is not expended or positive work, it's a negative work. Now next question D, what heat was added to the gas between B and C? So for that, again find out internal energy at initial B and final C, UB and UC. The equations are again U is equal to 3 by 2 PV. So UB is equal to 22,500 joule and UC is equal to 7,500 joule, and delta U is equal to UC minus UB, that is minus 15,000 joule. Difference of these two. And finally from first law of thermodynamics, solve for change in heat Q. This is the equation, delta U is equal to Q minus W. Put the values, Q is known to us, W is known to us, delta U is known to us, Q we can find out that is minus 25,000 joule. Negative sign shows that heat is absorbed. It is not rejected, it is absorbed by the system. The next question, what work was done by the gas from C to A? First we found from A to B, B to C. Now regarding C to A, what amount of work will be done? When you think about this, here change in volume is 0, delta V is 0. So what do you think about this work done? Yes, think. Work done by gas WCA is equal to area covered by CA. Now what is area covered by CA? Of course it's a straight vertical line, so it would be 0 because straight vertical line will not cover any area over this XY line, so that is 0. Now next, F, what heat was added to the gas between C and A? What would be the amount of heat to be added between C and A? First find out UC and UA, that is internal energy at initial position A and internal energy at point A. C and A, equation is delta is U is equal to 3 by 2 PV. So find out UC and UA. UC is equal to 75,000 joule, UA is equal to 22,500 joule, and hence delta U is equal to UA minus UC, that is 1500 joule, and it's a positive. It means that there is increase in internal energy. So finally solve the equation for Q. Delta U is equal to Q minus W, and put the values. Q is equal to delta U plus W. Delta U is known to us, W is known to us, hence Q is equal to 15,000 joule. That is, the heat is positive, hence it is added to the system. And then take the solution. Now next example, take the solutions from the last problem and find out these entities. The first one, net work done by the gas in the cycle, and second, amount of heat added to the gas. Now from this data which we have computed in the previous example, we have to find out net work done by the gas in the cycle. So this is the solution. The equation is summation of work is WAB plus WBC plus WCA, that comes out to be equal to 10,000 joule. Then total heat QAB plus QB